Thanks. Am I audible?
Yes.
Okay. Good morning, everyone. So today is our third lecture in this series. And in the first lecture, we learned some details of single dish. And in the second, which was the last one, we used how we can actually connect those single dishes in pairs, and we can build what is called a radio interferometer. And using radio interferometer, we could measure spatial coherence or the visibilities. So, in very simple terms, what an interferometer was, it was essentially a device in which the basic unit was an antenna, and we arrange those antennas such that by using Earth's rotation, we can very economically sample what we defined as the UV plane. And UV here, of course, is not ultraviolet. UV here is corresponding to the coordinate system in which we were measuring antenna separation, and for that we use the term baseline. And the visibilities that we obtain from this device then can be Fourier inverted to obtain the image. So what we want to do today is to see how we do it practically. Like what are some of the practical concepts involved. In the last lecture, for example, we understood some of the Fourier transforms things. We will apply some of them, and then some of the signal processing bits we will see, like how all these things come together, and we actually do a Fourier inversion and also calibration, which is very important because we need to correct some effects that corrupt the visibility that we are measuring. How do we do all this and can make images that are as real as at any other band? So that's the objective of today's lecture. uh, so so this is what we have been talking about, right? This is the quick summary. At the top, you can see that we have visibilities, and if we take a Fourier transform of this, we get intensity distribution in the sky. And since ILM is real, so VUV is Hermitian, which means that just from the measurements of VUV, we can also fill in the negative spatial frequencies. And if we take any antenna pair, and as the Earth rotates, the baseline corresponding to that antenna in the UV plane generates these kind of ellipses. And depending on at which declination the source is and how long we are tracking it, it leads to this kind of UV coverage. And this UV coverage is not corresponding to just one antenna, it's corresponding to very large array telescope in this case. And in that case, antennas are arranged along Y shape. And it's arranged along Y shape because that's one of the efficient ways of filling the UV plane very rapidly. So that's why antennas in this case has been arranged along Y shape. And then there are other configurations also in for arranging antennas. Then it all depends on like what kind of telescope or the interferometer that we want, and that would then determine how we want to arrange our antennas in that. And then we can take so these points are not actually the measurements. These points, which we call as UV coverage, represent the points in the UV plane at which we have made the measurement, right? And when then we take these measurements, take a Fourier transform of these, and we can get an image like this, for example. So this is an overlay of an optical image, and on top of that, in red, you are seeing the radio image. So radio here is corresponding to these giant radio lobes which are coming out of this AGN, which is here at the center of the image. You can see it in optical. So you can see how there is this nice complementarity here between radio and optical. There is this large synchrotron emitting plasma, which you would see only at radio wavelengths. And both these images are real, right? So this is how it all works out. So now, first step to make all this practical is to define a coordinate system in which we can define like how we are measuring the visibilities. So we on ground we define a coordinate system U, V, and W. You can see it here. U is generally defined with respect to along the east direction. V is towards north, and W is towards the direction of our interest in this case. And then on sky we have L and M direction cosines, which are measured for U and V, right? So that's the basic coordinate system. I'm not going to describe the coordinate system in great detail here. You can look into, for example, an arrow lecture series or any of the radio astronomy based textbooks that would give you how you can understand this properly. But what happens that if you take our VCZ or Van Sitter-Zernike equation and we translate this using this coordinate system, we can rewrite it like this. So on left hand side, we have visibility, which is measured in UVW plane, and then this is the intensity distribution, and then the rest of the coordinates appearing here. And you can see that this integral is actually extending from minus infinity to plus infinity, right? But of course, we know that the any intensity distribution that we measure will actually be coupled with the antenna power pattern here. So there is this another term that we need to introduce here as well. So this is the modified brightness distribution, that's what we always measure, right? And this we know very much from our first lecture where we were understanding single dish. And this expression in under certain approximations can be completely uh, reduced to a 2D Fourier transform. And those approximations are, for example, if I am having coplanar baselines, which means that all the baselines have only U and V, W is set to 0. And another approximation could be that I am measuring only a small region of the sky. I am imaging only a small region of the sky. In that case, this L square plus M square is much, much less than 1. In either of these approximations, these lots of these terms here in this first and the second term would disappear, and I would get a very simple 2D Fourier transform expression, and that can then just be inverted and I get an image. So you might be wondering what happens to the rest of the field of view. Of course, we routinely measure, make images of the entire field of view. I am taking this very simple case here to illustrate uh, some of the applications. It is outside the scope of today's lecture to go through some of the effects that we need to take into account if you want to image the entire field of view. That would come under the advanced imaging algorithms, but they can be covered in another set of lectures very easily, and they are very interesting, but something which we use very routinely. It's just due to the lack of time we are not covering them today. Okay. So once we have got this simple 2D Fourier transform expression, all that remains is to do an inverse Fourier transform, and I get this intensity distribution modified by the antenna power pattern, right? So, and this is very much my image, and this is what I get. So now let's bring in another practical aspect into it, which is that visibilities, here I represent them as a continuous function, but we only discretely sample them, and we discretely sample them at certain points. So I define what is called a sampling function here, SUV, which is a set of these delta functions. So the UV coverage that I was showing in this figure here is essentially showing up the sampling function. So these are it is one where I have a measurement, and it's 0 where I don't have a measurement, right? So this is what it is. So my visibility is nothing but a discretely sampled representation of this continuous visibility function, which I can write it like this here in the second step. And in a shorter form, I can write it like this: Vs, which is the visibility sampled, is equal to S multiplied by Y. V, sorry. Right. So now if I want to do a Fourier transform of this, right, this will be Fourier transform of S multiplied by V. And if I recall what my convolution theorem was, then my image will be just the convolution of Fourier transform of S, which is my sampling function, and Fourier transform of V, which is my visibility function, right? And if I had no sampling function here, that is, if my visibility was ideally sampled, then this my Fourier transform visibility will be giving me this image directly. But instead, what I get is called ID, and we call this ID because we call it dirty image. Why we call it dirty? Because it has certain artifacts which are coming from the fact that my visibility distribution has these holes, and it ends at a certain point, and it is sampled at only certain points and not continuously, right? And let's see what does this mean. So on very left, if you see, this is just let's say the sky, and it has got some point sources. There are 4 sources you can see in your screen, and in the second panel here, you see what is called the point spread function, or the dirty beam. If I go back to this expression here, dirty beam means nothing but the Fourier transform of the sampling function, and we call it point spread function as well, right? This is what we have here. So what my dirty image is, the convolution of these two. So convolution, again, if you have thought about it a little more, you would realize that it does not mean that it's a pointwise multiplication of these two. It's what you would get in outcome is that each source will actually show these impression of the dirty beam or the point spread function here, right? You can see that each source that we have here is having is multiplied with this, because that's what convolution is. So the problem that we get because of this dirty image is that we cannot make accurate measurements, because you can see that the artifacts that are coming corresponding to one source are actually falling onto the other source. If I try to measure the flux density, for example, of any given source, I will make an error in that measurement. So we need to do two things. One is that reduce the side lobes as much as possible. That's the first thing we do. And the second thing is that whatever the side lobes that are remaining in the image, we try to remove them. And we do both the things. So first thing, how do we take care of the fact that there are side lobes, and how can we reduce them? So for that, we know again from Fourier transforms last lectures that we can weight the visibilities. Why am I getting these big side lobes? Because my visibility distribution has got large holes, and it also ends abruptly at the outer edges, right? Because at some point my antennas don't have any more baselines, so my visibility distribution ends. If you look at here, there is a region outside which there are no measurements at all, right? So what I can do is that to choose a certain weighting function, which I write here as W, and that weighting function I choose such that it downweights any regions which are actually have poor measurements, and it also very gradually tapers the weight to visibilities as I move towards the outer regions in the UV plane. And as a result of that, what happens that the side lobes that are coming from the abrupt end in the visibilities, it actually uh, reduces. So you can see here in the top figure, which has 4 panels, it gives a measure of the point spread function for different tapers that have been applied. So the first panel, if you see, it is no taper. So you can see that the side lobes are so very strong here in this case. But when I apply tapers of different values, and these tapers are corresponding to Gaussian tapers, which means that the Gaussians of different full width of half maximum have been applied, and correspondingly the weights of the outer visibilities are reduced, you can see that the values of side lobes here are reduced drastically in this case. But at the same time, what is happening that since I'm reducing weights to the longer baselines, my resolution is also going down, right? So just using very simple Fourier transform properties we learned in the last lecture, we are able to understand like what kind of weighting that we apply to the data and what kind of effect it will have in my image. So I can choose an appropriate weighting depending on what kind of science I am interested in, and then how much reduction in the side lobes I want. So these are the trade-offs that I have to work with. And once I have decided that weighting, I apply to the visibilities, and then I do an inverse Fourier transform, and that's what gives me the dirty image, something like this here in the rightmost panel in the image here. And then after that, I do what is called the deconvolution. So deconvolution is what I try to subtract the point spread function which is there in the image, and that is something which we do iteratively, but we can do it very, very precisely. It is actually as precisely as we want. It just depends on how much computation we can afford to do in the process, and it is something which is done iteratively. What we do is that we pick up the brightest source in the image and take the point spread function, because we can compute it very accurately because we know the sampling function very precisely. I have the data, so I know at which points in the UV plane measurements are made. So I can determine the dirty beam or the point spread function. I scale it to the peak of this uh, bright source and then subtract it. But I subtract only a fraction of it at a time, because that's the accurate way of doing this process. And then I repeat this process on the residual image, and I continue to do it until I'm left with nothing but the residuals in the image or the noise in the image. At that point, I can stop, and then I will get an image which only has these point sources, but multiplied by or convolved with an equivalent Gaussian point spread function here, but no side lobes, right? So this is how I will get what is called a clean image, which will have no side lobes. And since it will have no side lobes, then I can go ahead and do all the accurate measurements of flux densities and sizes of radio source and all the properties that I want to determine. So this is how it is done practically. And then there are many variants of this deconvolution, many types of weighting functions that can be applied. You can look at this NRO lecture series whose reference I shared in the last lecture, and you can go through some of these things in greater detail. Like they're very interesting to do. So now let's talk a little bit more about sampling. What do we mean by sampling? Because that's something which is very important, not just at the time of imaging, but it is also very important to consider when you are planning your observation. Because by sampling here, we mean that how we want to sample our UV distribution and UV plane, and that would of course directly represent what kind of structures that I can have measured in my image. Because each baseline, as you recall, is measuring a particular Fourier component at that moment, right? And that corresponds to a certain scale in the sky. So when we talk about sampling, this is one very basic theorem that all of us understand, try to learn first time, which is that if there is any continuous band limited signal, and if I want to reconstruct it, then I must sample it at an Nyquist rate, right? And if I don't do that, then the higher frequency components will be aliased to the lower frequencies. And what does it mean in our context? Let's try to understand it from the simple cartoon, right? Let's focus only on the top uh, cartoons at this point. So first one, if you look at it, is just some arbitrary representation of visibility VU, and we are considering only one dimensional case just to keep everything simple and not get confused. So now if I want to sample it discretely, for that sampling, I can use sampling function. This is called SHA function, which is just a set of delta functions. It's an infinite series of delta functions having a separation delta U in this case, right? And if I take, uh, if I multiply these two, what I'll be left with the values of this visibility function at the points where I have this delta function, right? This is how I have discretely sampled this function. So now what does this mean in the corresponding Fourier domain? So now we come to the lower set of figures. Now corresponding to visibility, I have, let's say, intensity IL here. And let's say this is how it looks like it's some kind of a double hump kind of thing you can see. And the SA function, now we know again from Fourier transform, will again be a series of delta functions, but now the separation will be 1 by delta U, right? So if it was more closely spaced in one domain, in the conjugate domain, it is now a little bit further apart, right? So since we have multiplied while we were sampling, what we will do is that we will do a convolution here in the conjugate domain. And this, and the last figure, if you see, this is what it will look like. And if I have, so what I end up with multiple copies of my IL in this case, the intensity function here. And if my sampling was good enough, I will find that my these multiple copies are well spaced, and I can just apply a simple box function here, or I can do a convolution with its Fourier transform in the other domain to get this information completely. But let us say if that is not the case, and I have actually inadequately sampled. Let's say I used a sampling function here in red, which is much further apart. Then what will happen in the corresponding domain, if you look at the last figure, that these multiple copies that I was having are now actually overlapping with each other. So in the overlapping region, I have lost the information. This is what we were referring to when we are talking about the aliasing, that if I have inadequately sampled in one domain, then I will start losing the information here. Okay. So this is very important to understand after convolution, just to understand what the sampling interval should be, and then what it would mean to, if I am not adequately sampled, then it would lead to aliasing. But once this is taken care of, the visibility so sample can be Fourier transformed to obtain the image. And in our context, avoidance of aliasing will require that the sampling interval that I am choosing, delta U, that it should not be greater than the reciprocal of interval in L, like in the image domain, over which the intensity is non-zero, right? And if that is not the case, then the intensity from the outer regions would be aliased back into my image. So that's something which we want to avoid completely. So if we take care of sampling, we are left, but we will still be left with some holes corresponding to missing information. And then, of course, longest baseline will limit the resolution of the image. But apart from these facts, we now understand overall that how we can weight the visibilities appropriately and can actually make an image by inverse Fourier transform. But how do we do this Fourier transform? Like, how do we take these visibilities and do an inverse Fourier transform? So this is the expression you're seeing in your screen. And we can do something which is called direct Fourier transform, but that is something very, very computationally expensive. Okay, and if we are talking about an n by n image, and then order of computation that we are talking about, they scale as n to the power 4, right? That is like quite, and we are talking about data sets which have like many millions of points in no time, right? So interferometers produce large amounts of data, and we will see an example too of that. So this becomes very impractical. So instead, what astronomers use is called fast Fourier transform, FFT, and then there are various algorithms of it. One of the advantages that it gives is that now the computation scales at n square log n. No longer it is fourth power. So that is what we are after. But okay, there's a typo here. What FFT requires is gridding, not grinding. It's an autocorrect thing here that has happened. So what gridding means is that I need to sample my visibilities onto a uniform grid. That's what the requirement of FFT is, and that is something that can be done. But what it requires is that I must then because my visibilities are not uniformly sampled, then I need to interpolate across the measurements to ensure that they are I obtain them on a uniform grid, and that this entire process of gridding is computationally very expensive, but it is very interesting. So if you're really interested in imaging problems at radio wavelengths, the sampling and gridding are the two concepts that you really want to understand, and they are very interesting. So this is just imaging as a whole, but we have not yet considered so far what happens to my measurement itself. Up to this point, we have been thinking that, okay, I have a measurement and I can do a Fourier transform and I get an image, right? But is that all? No, that's certainly not the case, because any experiment that we try to do, our instrument has got certain gain, that the setup, and what this means is that any input signal that I am trying to measure from it will be modified by the instrument. And if I want to recover the true system, true measurement, then I must actually do what is called calibration. So the process of calibration is to remove the system's response. And how do we do that in all the cases is that we feed the system with a known signal. Because when we put in a known signal, we know what the output should be. And from that, then we can actually go backwards and try to calculate what is the gain of the system. Since we know the gain of the system, then if any unknown signal comes in, I know that what is it that I should do to recover my true signal out of it, right? So that's the process of calibration. That's true for every experiment. So, and we need to do the same for an interferometer also. So this is the expression here. So on extreme right, we have true visibilities, V true. They get modified by the gain of the interferometer. Ij represents here I and J antenna. So let's say we are talking about a particular baseline, then antenna I and J will introduce their gain into it, and then I am measuring certain visibilities. So those visibilities we observed are not true visibilities. I need to do calibration to recover V true. And in addition to this calibration problems, I can also have some bad data sitting into my visibilities as well. So I need to examine my data and then remove from it anything problematic which was there. So all this is like applicable to any type of data processing that we do, even in our laboratories, certain experiments. So we need to remove bad data, then we need to do calibration, and then we get the true measure of the physical quantity, and that's what we do our science with. We are not going to talk much about what kind of bad data editing that we need to do. We are going to focus only on calibration. So before that, let us see what is important in the data in this context, right? So on left we have an image. It's a sort of a top view of a city And if I take a Fourier transform of this, you can see there's something on the right, right? So what I do is that I take only top, let's say 12% of the components, and I don't take all the components from this right hand image, and then I do an inverse Fourier transform, and I get an image, right? And you can see that it already looks very much like what I started with. So most of the power is concentrated in top 10-15% of the components, and I can even reduce the number by half. Like if I take only 5% of the components, I still take something, uh, get something which is actually very much like the original, right? So this is the first thing that you understand, that in signal processing you need to understand that where the power is lying. Like if it's only a few of the components, then you need to worry about them the most and not everything else in your image. Now this is talking about phase and amplitude. Let's go a little deeper into it, and especially phase and amplitude we should consider, because visibilities we are dealing with are complex, which means that it has two quantities, amplitude and phase, right? So on left side you have an image of a clock, right? So we do two things. First thing is that we take amplitude part of this image and just randomize it completely, and do but keep the phase as it is, and then I do a Fourier transform, so I get something which is shown in the top right image, and it still looks like clock, right? But if I do the reverse, which is that I take the phase and randomize it but leave the amplitude as it is, then I get what you see in the bottom right image. This is like complete noise, nothing in it. This is another example. So on top I have a clock, top left or top right I have a picture of a city. What I'm going to do is that take the phase of each image and swap them, right? And then when I do an inverse Fourier transform, I find that actually the resultant image is actually corresponding to uh, the image from where I had taken the phase, right? So if you take the bottom left image, this corresponds to the image which had the phase information from image A, right? So it still looks like a clock, right? Even though the amplitude are coming from the image B. So what we understand from these examples, that amplitude is important. It represents the magnitude of the spatial frequency, but phase represents its location, that how the power is distributed, right? So if I want to have any resemblance to what I started with, phase term is really, really important. So in uh, radio interferometry, when we want to make image, we have to pay very close attention to how the amplitudes and phases are getting calibrated and what kind of errors they are getting affected with, because what happens that they both also get affected by different types of errors, so we need to pay attention to them. But there is a complete mathematical formalism to deal with this, and it's not something which is very arbitrary and we have to make ad hoc assumptions about it. So let's try to understand what that formalism is. So on starting with the left, so I have a transfer electric field, which I can represent it like this. Right, Ex and Ey, and it will get modified by propagation. And this propagation is through ionosphere, troposphere, anything intervening in the space. And it will also get modified by my telescope, its electronic chain, all the receivers, all the amplifiers that I have put in by the correlator. Everything is going to put something into it, its gain into it. And some of it will affect amplitude, some of it will affect phase, right? So I will get with something called E prime, Ex prime and Ey prime. So this translation from E to E prime I can represent by something called Jones matrix, right? And since there are a large, there are a series of effects, I can have a sequence of Jones matrices which define these various propagation effects. And what these propagation effects could be, for example, start with I can have a simple propagation, like it's called K Jones. This is just the phase term getting introduced as the signal is propagating. Then we have P Jones, which is like the parallactic angle. This is coming because if I have an alt azimuth antenna, then my telescope is rotating, reflector is rotating as I am tracking the source in the sky. Then as the radiation passes through ionosphere, then I can have Faraday rotation that's represented by F Jones matrix. Then I have G Jones, which is representing gains of the matrices. So you can see that they all have different properties. Some of them commute with each other, some of them not. But I can stitch all of them together in the order in which they come into play. And then if I can measure them or solve for them, then by applying them, I can recover my true visibilities. And that's how it is done. So again, if we start with like VP prime is my modified visibility for a particular antenna, and that is JP-EP. JP is the Jones matrix, and for another antenna, I have a similar equation labeled as Q, right? So now what does correlator give me? VPQ prime, right? This is a modified visibility, and I have just multiplied these two here, the second one being the complex conjugate, and then this is just using the simple matrix algebra, I get this equation. VPQ here is the true visibility, right? So this equation is called measurement equation of radio interferometry. So all the essence of calibration and the process that I need to carry out to recover true visibilities, in this case VPQ, is captured through this. So calibration is nothing but determination of Jones matrices in this case. And what this means is that, and determination of Jones matrix is different for different matrices. In some case, it is I have to just compute parallactic angle, so I just need to know some geometry. In some cases, I need to solve for antenna gains, and this is done by observations of calibrators. By calibrators, I mean that we observe sources with some known properties. That's I know how strong the signal is, what does it look like, which means that what kind of amplitude and phase my interferometer will show, and using that, then I can solve for antenna gains. So this is this large G Jones I can determine, and then in some cases I will have to have some external help, like for example from GPS, through which I can measure the properties of ionosphere and determine this F Jones matrix here, right? And once I know these matrices, then I can use simple linear algebra to solve for antenna-based gains, which can be applied to my corrupted visibilities to recover the true visibilities. That's the total process, right? So you do measurement, you do a calibration, and then after that you go and do the imaging. That's the process. So now again, if we go back to our first lecture, we had estimated what the sensitivity of a single dish was like. We defined a quantity system equivalent flux density. Now sensitivity of an interferometer would be like this. You can recognize most of the terms except that this new term n appearing here. N here is corresponding to n antennas or n dishes which I have, which my interferometer has, and n minus 1, 2 is actually the number of baselines that such an interferometer will produce. So the sensitivity is like now getting contributed by all the dishes that I have put into place, right? So I am not only getting resolution here, but I'm also gaining in sensitivity in this case. But another complexity that we have to deal with when we have interferometer is that we end up with large volumes of data, right? And it requires enormous compute power to make images using interferometer. In case of single dish, it was just one dish and I'm getting just a data stream, but now each antenna pair is producing a visibility at any instant. So if we take, for example, Meerkat telescope, I'm giving example of Meerkat because it's now the most sensitive telescope at centimeter wavelengths. It has 64 antennas. It has 856 megahertz bandwidth instantaneous, that's huge, and it has 32K frequency channels. So each one of these, if it produces a data point or visibility at an instance, and I collect them after 8 seconds of it, every 8 seconds, then it produces 1 terabytes in an hour. And an observation typically can last few hours to 8 hours, right? Or 10 hours. That's the time usually, like if you want to observe an object from its rise time to set, because that would fill my UV plane completely as much as possible. If I do that, then I would end up with something like 10 terabytes of data for observation of one portion of the sky. That's a really large amount of data that we have. So now in rest of the talk, I want to talk a little bit about square kilometer array, but I also want to give you some ideas and I want to make some general remarks so that we don't go away with some misconceptions here. In the first talk, in the first lecture, we started with the idea that okay, dipoles are not so good on their own, right? But I use the term on their own, right? because they don't have enough sensitivity and directional properties. But especially if we take an array of dipoles and I'm operating at lower wavelengths where they are large enough to offer substantial collecting area, by combining these dipoles, we can form what is called multiple beams. So there's a concept of beam forming, which you would want to understand if you want to know how these are used. And then I can introduce a phase at each of these dipoles, which can actually alter the direction in which it is looking, right? And that is called electronic steering. So at low frequencies, for example, 100 megahertz or 2 megahertz, the preferred technology to do interferometry is not use dishes, but it is to use actually a set of dipoles, which are combined through beamforming, and we observe different parts of the sky using electronic steering. And there are telescopes like this, like LOFAR in Netherlands, which is one of the most sensitive low frequency telescope, along with GMRT. And then there's MWA in Australia, which and you may want to look at these telescopes in more detail, that how the concepts of interferometry get applied in this domain. And since we are talking about dipoles which can be combined or phased, we talked about parabolic reflectors having a dipole as a feed, but we need not have a single dipole, right? We can have an array of dipoles, which is called phased array feeds, which can actually then be used to dramatically increase the instantaneous field of view, right? You can look at the example of Australian square kilometre array pathfinder ASCAP, which uses a phased array feed. And what happens in that case, that if it was just a single dipole, it would give you a field of view of 1 square degree. But using a phased array feed, it actually gives, it is possible to get an instantaneous field of view of 30 square degrees, right? 30 times increase, which, and it's tremendous actually, because the goal in astronomy is to go deeper in sensitivity, to look at fainter and more distant objects, and also to be able to look at large portions of the sky, because so that we can collect very large samples of galaxies and AGNs and stars and everything, because that then allows us to understand statistically how these different celestial objects are evolving as the universe evolves, right? So these are some of the key points to keep in mind, that different receptors and technologies are used at different wavelengths, right? This is key too. We don't just take one thing and try to apply it at all frequencies. One study is like, what will be the most optimal technology for this wavelength or for the science, and that's how the telescopes are designed. And correspondingly, calibration and imaging recipes can also be different, because as you know, we go towards the lower frequencies or the longer wavelength, then ionosphere starts to play a much more dominant role, right? And at the higher frequency, it's the troposphere. So the kind of Jones matrices, their relative weights actually would change, right? And similarly, the kind of imaging algorithms that I may have to use would change also. But the basic concepts will remain same, and most of them, at least at the superficial level, we have tried to cover in these 3 lectures, right? So I hope that anything that you now try to read on these topics would at least appear familiar to you as you start with. And of course, then you'll have to work out the algebra and go deeper into that. So this is now a very exciting time for radio astronomy currently, because uh, international community is building what is called Square Kilometre Array, which will be the largest radio telescope in the world. And in India, we are also very excited, because India is one of the country which is part of this international consortium. So what is SK? I already told you, this will be the largest radio telescope. And in this graphic, you see that how the different telescopes sensitivity is compared with, and SK will be enormously more sensitive compared to these. But an SK will be built in 2 parts, right? One part will be called SK mid, which will cover higher frequencies, and another part will be SK low, which will cover lower frequencies up to 300 megahertz. And the lower frequency component will be built in Australia, and it will be built out of using dipoles. You can see in the top left portion of the screen what they would look like, and whereas the higher frequency component in South Africa would be built out using dishes. And since this is going to be so huge and so complex, that community is building it in phases. So first phase is called SK1, which will have the 10% sensitivity of the full SKA. And when this is completed, we would have understood the complications that are coming at different stages of uh, the telescope, and those can then be dealt with as we scale up uh, and try to build a full array, right? So that's the idea. And SK1 should start construction in a couple of years. And you can visit SK site. This link is given here, and you can try understand about both the different telescopes and what kind of science they will do. This is a video showing how SK made when it's built in South Africa. And you can see that one thing that you will notice that, okay, large number of dishes, but also it's a site where there is nothing else except the telescope. So again, we understand that why we go to such places, because we want to avoid radio frequency interference completely, and we want to build telescope at a site where we can get clean signal from space. Now this is a similar graphic, but now for low frequency component. This will be built in Australia. So one has gone to Australia and South Africa because it was possible to get such remote sites, such large areas of peace, of land where there is no civilization there, no people living there, right? So you can see that the similarity of the sites, both are remote, but then also the differences in that kind of antennas used here, right? And this is now demonstrating how SK1 will be better compared to some of the best radio telescopes. So the comparison is made between LOFAR and VLA in the central figure if you see here. So what is compared here in the left one is the resolution that would come. You can see that the kind of resolution that SK will produce and the kind of resolution or the clarity that the current telescopes are producing. And then on the rightmost, you can see the kind of difference that will come in the sensitivity, right? So you can look at the numbers also, 8 times more sensitive and 5 times more sensitive compared to LOFAR and VLA. And in terms of resolution, again, like it is much more there. So what will SK do? So there are several key science drivers for SK, because when a telescope like this is designed, people already think about like what kind of science we want to do it, because that the science to be done with a telescope forms a justification, or is the main justification to build a telescope. So SK will be so sensitive that it will touch upon every field of every branch of astronomy actually, whether we talk about galaxy evolution, whether we talk about tests of theory of relativity or magnetic field, how it evolves in different celestial objects or intergalactic medium, then very early stages of the universe, cosmic dawn, which is like very first stars and galaxies, and also the cradle of life, which refers to the fact that searching for planets where actually there may be some life. So looking for those extraterrestrial intelligence or the civilizations. So in India, like especially at IUCAA, we have a lot of interest or engagement with Mica telescope in South Africa. We use GMRT a lot, but now we are starting a very large survey with Mica telescope. And why Mica is special? Because it's a precursor telescope to SK, which means that currently Mica has 64 dishes, but when SK1 is built, which will have many more dishes, close to 200 dishes. It will be built out of Meerkat telescope. And already Meerkat is the most sensitive telescope at centimeter wavelengths. At IUCAA, we now have access to Meerkat telescope. We have a large survey to be carried out with Meerkat, that's called Meerkat Absorption Line Survey. The total time that we can provide to this survey is like close to 1700 hours. So that's a huge amount of time. And the main objective of this survey is to study the evolution of cold gas in galaxies. And there's a whole range of science cases that it will do. And you can look at more details of this using this http://maths.iucaa.in. And this project is led by me and Shianand at IUCAA, and it's an international collaboration that is trying to use this data to address a whole range of science cases. So if you are visiting IUCAA and if you're interested in any of these projects, feel free to write to us or chat with us. So this is pretty much the end of my slide, and this is where I will stop. And we can take some questions. We have good 10-15 minutes or so. So thanks a lot for listening and your interest. So I will stop sharing my screen now. And first, let us go to the Google Doc. Come on, or let me just go to chat first. So if I stop sharing, it becomes easier. Okay. Okay, so Fourier Transform localize the source, ignoring the noise. Not, I would. So question here is the Fourier transform helps us to localize the source, ignoring the noise. No, we don't ignore the noise. Noise is always part of the signal. What Fourier transform is represents here is actually that you have to then think of it in conjugate domains, right? So what a Fourier component in this case, like if I take an antenna pair, is measuring a particular scale in the sky, right? If I take two antennas which are very close by, then it is a measuring Fourier component corresponding to the large scale distribution of the intensity in the sky. But whereas if I move these antennas far apart, then I will become sensitive to the fine structure in the radiation in the source. So I take all these Fourier components together, then I have all the details which are there in the source that is there in the sky, right? So like the 30-meter telescope, while we are using discrete component pieces to join over forming a big lens, can we do it like the same in case of, yes, of course, that's how it is done. Like if when I was trying to explain large single dishes, it's impossible to build large dishes of tens of meter with just as a monolithic structure. So the way they are built is that we build different panels, smaller panels, which can then be stitched or assembled together to form a parabolic reflector. That's how they are built. And it's the same complication which comes in a case of optical mirrors also. And there also, since it is not possible to build a single big 30-meter mirror, one will build smaller pieces and then they will be assembled together to sort of make the big lens or big mirror. In both the cases, the problem is that as the whole structure becomes so heavy and it starts tracking the object, then how do we actually how does it maintain its shape? So in case of TMT, since it's operating at very uh, short wavelength like angstroms, we are talking about thousands of angstroms. The placement of those mirrors need to be maintained at very high accuracy. If we go to lower frequencies, especially very short wavelength, then it does not really matter. For example, if you go to GMRT, you would find that the dish there actually is not even solid. It's actually made of a mesh, and but to the radiation that it is reflecting, it appears as a solid surface, right? Because it operates at wavelengths which are longer than 21 centimeter. So the tiny holes which are there in the mesh actually uh, do not appear to that radiation. It just acts as a solid surface for that. But the advantage then we get by putting in mesh there is that the dish becomes very light, and then it's easy to maintain, easy to for it to track, it's easier for it to maintain its structure as it sort of tilts as it's tracking different kinds of objects, or if there is strong wind, then wind load is also lesser. So these are some of the clever things people do depending on how we are actually as we understand like at what wavelengths we want to operate. Okay, now the question, in the imaging step, every visibility point is given a weight. Yes, it does. Is it a uniform or a non-uniform weight for all the points? What difference does it make? Yeah, that's a very good question. So so first is that, okay, if I want the maximum sensitivity in my map, that then I would give all of them same weight, which is the weight of 1, right? That's the natural weighting, I call it, right? And that would give me a certain image. That image may be good, that image may not be very good, and that would depend on my initial sampling function, that how does my UV coverage looks like. But let's say if my UV coverage had lots of holes and also it was sort of ending abruptly as it generally happens, then I would end up with large side lobes or larger noise in my image because of those issues, right? So in that case, I would want to reduce the side lobes in my image. In that case, what I would try to do is that as I'm going outside in the UV plane, I will try to give those baselines slightly lower weights. Okay, and since I'm giving lower weights to my data, which means that I'm not using all my data completely, the noise in my image will go up, but the artifacts will go down, the side lobes will go down. So it's quite possible that I may actually end up with an image which was better, or is better overall. It has a better fidelity compared to the image when I was giving uniform weight to all the data points. So yes, we do change weights of the data when we make image, and these are not uniform. These are generally non-uniform weights, and that depends on what kind of image I get. I can also do some more clever things. For example, let's say if I want to make an image which only has information about the compact structures which are there in the sky, then I can give very small weights to short baselines, and large baselines can have very long baselines can have very large weight. And I can do the reverse by giving small weights to longer baselines. Right? So that kind of games astronomers play to make different kinds of images from from the same data, right? And this is something which is very different from optical astronomy, right? Because in optical astronomy, lens is fixed. You just get it. You get your image and you're done. You can only maybe reduce the resolution by smoothing it. You cannot do more than that. But in radio interferometry, what we are doing is that we are actually doing the Fourier transform, and at that time we are actually building the lens, right? So the kind of weights that we give to UV coverage which determines what kind of lens we are building, and correspondingly the image properties change. Yes, if we get uniform weights, we are getting finer details. You're right about that, but I will request you to try to formally understand what is the meaning of uniform weights in this case. Okay, but you're right. So next we go to Google Doc. So if there is so while I'm answering, we have a few more minutes here. So if somebody wants a particular reference or something on a particular topic, I can tell them now. Right? Please feel free to ask more questions on the chat. I'm right now going to Google Doc, and I'll come back to chat before we close. Okay, so now this is the link to Google Doc. Okay, so Google Doc does not really have any clear questions. So okay, so there was nothing on YouTube chat. This means yes, absolutely.
Yeah, I guess. Did you get any chart?
No, I am getting some more questions which I can answer now. People are asking for references, and that's a very important thing at this stage. So I'm going to share my screen again and give it to them. Okay, just a moment.
Sure.
Okay, so here now you can see my screen. Okay, I can also open the chat at the same time. Right now we are set. Okay, so these are some of the basic references which I had shared in my. So Bracewell, this is for Fourier transform and its applications, but you should also look at some signal processing books at the same time. And that would give you a slightly different perspective on it. But Bracewell is very exhaustive if you want to learn Fourier transforms formally. Then Born and Wolf for principles of optics is really very good. And then you can look at also Jenkins and White especially like if you think that you want to first brush up basic idea of how the ray optics and wave optics work, and then you want to go to more mathematically intensive Bond and Wolf, right? And specifically for interferometry, you can look at Thomson, Moron, and Swenson. This is interferometry and synthesis in radio astronomy. It uses a lot of engineering jargon, but it's really, really good actually. And you can look at synthesis imaging in radio astronomy. It's an NRO lecture series, and PDF of this book is available online actually. So you will find it very easy to access it. The only slight issue with this book could be that you may have to do multiple reads of this because it's a lecture series, right? So they are assuming a certain level of understanding or familiarity with astronomy already. So you may find that, okay, you have to go through some of these things more than once before you start making sense of what is going on, right? Because it's sort of lectures which are sort of cross-linked many times. But again, it's really very good. So you can look at these 4 books definitely. And then you can look at Tools of Radio Astronomy by Rolfs, right? And I will also try to write it on chat so that you can see my screen. My screen is shared, right? Let me write it on my slide directly. We'll have better. Okay. This will also give you a lot of information on antennas, and also the Thomson, Moran, Swenson book would give you a good deal of information on antenna, different types of antennas. You will get it there. But all these are either optics books or interferometry books. So if you want purely about antennas, then you will have to then go and fetch some books on just talking about antennas in that case. Okay. And look at some books on Fourier optics, I would say. There are plenty of them that you can get. And they're really interesting to read, trying to understand how uh, basic optics work. Because whether it's optical imaging or we are talking about interferometry or imaging with single dish, the basic concepts, as you can see, are very much same there, right? So if you do a bit of Fourier optics, you do some signal processing, and you know a little bit of linear algebra. All you need to know after that is just to program, right? And if you can program right, you are an astronomer already. Then all you need is actually some interesting objects to look at. So while you're doing all this, don't lose sight of open sky, right? That's really important, because you don't want to be in a situation where you have an excellent telescope but don't know where to point it. But I have tried to cover many things in these 3 lectures. You may be thinking that I could have done maybe only one thing, but I wanted to really give you a broad flavor of the different type of things that we use in radio interferometry, starting from basics of Fourier transforms, Fourier optics, then knowledge of antennas, engineering, then electronics. We did not talk about receivers at all. That's something which is really interesting as well, that how to have good receivers and how to keep their noise low. But we touched upon some of the aspects, so you can understand that like it's a lot of engineering involved there in designing dishes and electronics chain. But once we do that, then we get large amount of data and we need to calibrate it. That's a lot of software engineering and linear algebra required. That time signal processing knowledge is required, and then of course once you get those images, then you have to know your basic physics to understand what is going on there. So this is also the I think 11 o'clock. So I do not see any more questions here on the chat. So thank you all for joining, and thanks to everybody behind organizing this, our IT team as well as TLC, who have been curating all the questions and who have been sitting Thanks everyone. Thanks to all of you, all the students.